So parallel execution with Dagger. So in this session, we'll look at Dagger, and specifically how to execute these like task graphs with Dagger. And that's when a task has so when we have multiple dependent computational tasks, so that we have to execute some tasks before we can execute some other tasks. Then we have the dependencies, but then we have these tasks may be independent, in which case they can be executed in parallel. And Dagger can help us to automate this and execute tasks in parallel using processes or thread processes. But we'll see that a little bit later. Dagger can also do other things, but we don't discuss them in this lesson. Like there's like out of core computation things. If your data doesn't fit into memory at once, then it needs to be processed in chunks. Things like that as well. But I will start with a little bit of theory, a very little bit. But task graphs are based on the concept of directed acyclic graphs. There below you can see one, but this can be used to model dependencies between computational tasks. In the graph you see below, you can think that it's one of these nodes or vertices is some computational task, and these edges model the dependency between the tasks. For example, the task 2 is dependent on the task 1 being completed, and also like the task 3 is dependent on the task 1 being completed. However, the task 2 isn't dependent on the task 3. And this means that when these tasks are executed, we would first have to run the task 1, but then we could run the tasks 2 and 3 in parallel. And then finally it would run the task 4. And these task graphs can be very elaborate, very complicated once you have more complicated scientific workflows. And this is also a common way to represent and think about scientific workloads as this kind of task graph where you have tasks that depend on output of the previous tasks, but then we want to efficiently execute them using all resources available in parallel. Anyway, here's a kind of formal way to put this. Think about that. If there is the dependencies can be thought as kind of this path. So if you follow the arrows here, you have like this path from 1 to 3 to 4. These tasks are dependent on one another. Same thing with that 1, 2, and 4, but the 2 and 3 aren't, so they are independent. And moreover, it's the other thing is important to know that usually in very complex workflows, we don't necessarily know this task graph before computing. There are some frameworks that can assume that we know what we are going to execute, like what the full task graph looks like before we are going to execute it. But that isn't the case usually. And these are usually this kind of dynamically generated task graphs. Think of that if the amount of kind of dependent tasks in the kind of step 2, but if it would depend on the output of the task 1, there could be variable amount, and we don't know before computing. And the nice thing is that Dagger can handle these kinds of dynamically generated task graphs as well. And also Well, for Python, Dagger is similar to Dask in Python, which also can do this kind of task graph execution. I think they're going to pick up ideas from Dask into Dagger. Construction noises here. But yeah, let's look at Dagger and how it works and how we can put these Dagger workers and run various task graphs in parallel. So you can start Julia with 2 threads. You can do this on your local computer or in the cluster. Even logging node is probably fine for this one, whatever works for you, but local computer is fine. Modern computers have enough threads for this. And then assuming that you have Dagger installed, you can run commands to install Dagger. I should have it installed yesterday, so no need to reinstall it. Now our main Julia process is running with 2 threads, and Dagger can use threads as workers, but it can also use processes as workers. So I'll also use the distributed virtual. More processes, specifically we'll add 1 new process with 2 threads, so that we'll have also 1 worker process with 2 threads, and then we'll see how Dagger creates us some workers. Also, we want to import Dagger after specifying the workers and use the everywhere flag so that all processes load the Dagger package. So now we can get handle on this context of data structure from Dagger, and from this data structure we should do it has this prox value that has a vector of Dagger processes, and here we have 2 of these OS processes. One is running on the main Julia process, and the other is running on the distributed worker process too. But we can get even more information because we actually have even more workers, because we also initialized both of these processes with 2 threads. If we use this get processors from the CTX proc, we can query we can get the set of these thread procs that we have, and here we have in total 4 thread processes, and that is 1 for each thread on its worker. And Dagger will be able to use all of these to execute tasks. Next, in the example, we define the task function. Here's very simple. We return the worker ID and thread ID just to see that where does this task execute. And we also need to use the everywhere macro so that we load it on, so that this task function is available on all processes. And now we will use Dagger to spawn 10 tasks. And now there's some Dagger tasks. We can fetch the results and print them. Well, it prints them here, but if we if you look at we execute the task as such, we see that the kind of main process is the thread 1 or thread process 1 or thread 1. And when we look at where did all our work execute, it executed on actually on all the other thread processes. So in fact, it actually Dagger uses the worker, the thread 1 on worker 1 as this main process to run Dagger and run the scheduler, and it executes the tasks on all the other thread processes. And here's a bit more elaborate example that dynamically generates these tasks based on the outputs of previous tasks. I will use the random module to create some random number generators so that it will randomly generate different numbers of tasks. And then we have this nested task that, and this is also an important thing in Dagger, that we can spawn new tasks from a task. So when Dagger is running something, it can still spawn new tasks. Then we create some random generators. And finally, we will create these tasks. And you can see that the task A and B, they run first, and then task C is dependent on the output of the task A and B, and it will generate some random number of new subtasks, which then will be fed into the task A, which also takes the output of the task D. So this showcases a bit more like complicated task graph execution. And then we should be able to specify the result. Anyway, that's a relatively short section, but there's an exercise here where you will be required to add some spawns and I think everywhere statements to make this task graph execute more parallel.
So move now to the how to run Juliana HPC cluster. We'll of course be using Lumi for the demonstration here, but running Julian different clusters is pretty similar, unless you have some very kind of heterogeneous processor architectures, then the setup might be a bit more difficult, but typically it's like the simplest setup of Julia is just downloading the pre-built binaries and running with those. Anyway, yeah, we'll look at how to run Juliana cluster and parallel computing on a HPC cluster. I'll first have a little bit of a HPC terminology, just so that we are on a same, we have the same terminal, or like everyone is acquainted with some of the basic terminology on an HPC system. If you have been using HPC systems, these are probably familiar to you. And also a little bit about Juliana HPC systems. So yeah. Julia is not really yet considered as kind of mainstream language as C or C++ or Fortran in the HPC world, but the nice thing is that Julia can do very high performance, or it is a high performance language, and it has been used in the kind of beta scale computations, and definitely better than Python, of course, which is still more commonly used, usually to interface to the lower level languages. And about Julia cluster, Julia is very simple to run on a cluster because if you have a ready-made module environment, then it's just loading the module. The module should be very simple. The modules that I've installed into CSC are the Finnish national clusters, and on Lumi, the Julia module should pretty much load the pre-built binaries. If you go with the Julia downloads page, you can download what are the latest binaries for the right architectures, and that should work. And that's pretty much it. If you're installing Julia, another thing I've added to the modules is just that it sets the thread count based on the requested Slurm CPUs per task. But that's merely a convenience. You can always set that variable yourself or provide the right Julia flags to how many threads you want to use. There's not, it's very simple. Or if it's not a Slurm cluster, you use some other environment variable or something like that to determine how many threads you want to use. But and the reason that Julia is simple to install, because Julia itself is a compiler, so it's not so critical that Julia itself is compiled with all the optimization flags possible. That speed ups are only the only place that it affects the speed ups is usually just compilation speed, and those are very trivial speed ups. So it's better to have install just the pre-made binaries, which are easy to install across platform, and it's very, very fast to install Julia. There is this Julia for HPC GitHub page. We can look at slide very quickly. It has some tips on running Julia on HPC cluster, and also for installing it, and some systems that have a Julia support. There are some tips if you happen to have some problems or you're just interested. You can look this up, but this is mostly useful for administrators, or if you're running it on some very there are some cluster that has heterogeneous processor architectures and stuff like that. There are a few other cluster or considerations for Julian cluster, like where to install packages if you're installing them, what you want to change to something else than the home directory. But let's move on to the HPC terminology. So HPC cluster is the network computers. We call the computers nodes, and these nodes are typically separated into the user-facing logging nodes, and then the compute nodes that are intended for the heavy computing. And what defines HPC clusters is that these nodes are co-located and connected using a high-speed network to minimize communication latency between the nodes, which maximizes the performance at scale. And clusters also have usually a parallel file system, something that provides a system-wide mass storage capacity. This is usually accessible from all the nodes on the cluster. And this is like a Lustre. Lustre is a common parallel file system, but there could be others. They could also have node local storage, this kind of fast memory. Clusters, every cluster pretty much uses Linux. So understanding or Linux knowledge always helps for a lot of issues on a cluster. Although clusters do have some special software like the cluster for the storage and the module environments and workload managers. And the module environment is used to manage software environments. These are kind of user-facing components usually with the module load that you can load some software. And Julia may or may not be available depending on if it's installed into a cluster. The Julia for HPC site that I showed some sites that have pre-installed Julia, but you can always install Julia yourself and manage it yourself. And that might be a very good idea if you always want the latest Julia version, and especially if you're using things like GPU, MPI, something that's very sensitive to configuration. And module environments, the most popular module environment software is this Fortran. It's a Lua library for loading environments. But we'll see that a little bit later. I guess you have already touched the module command. And also, finally, the HPC clusters have a workload manager that manages the resources and run jobs on the compute nodes. And most popular of these is Slurm. And we can also use Slurm to run various Julia programs and do parallel computing. And a single workload run using the workload manager is usually called a job. Let's move on to module environments. But we have a couple of commands here that we need to be aware of. So the base command here on the left side on a Lumi cluster is the module command, and it has a number of subcommands. Oftentimes you just use module load, and then you have a bunch of modules that are on this module path, or it finds all the modules that are on this module path. But sometimes your software is not on the default module path, so then we can use this module load, which we have already used. Here we add some path to a directory that contains more directories that have these Lua module definitions that are the modules that you may want to use. In this case, we use this CSC local module files where I've installed Julia. And we can query availability of different module versions. Here we should see a list of Julia versions and a few other Julia AMD GPU and MPI module. I'll explain those a little bit later. This might take a little while on the cluster. If something takes a while, it's usually the parallel file system because it does some file system operations, but the parallel file system is this client. It's like the server client architecture, so it sometimes lags a little bit. It's not as fast as on your accessing file system on your own computer that usually have like SSD. That should return the values soon. If you want to see what's inside a module, you can use this show command. Okay, now it loaded. Here we have various Julia versions. This is the latest default. That's a default module is not sure the L. Okay, that's why it's loaded. they have a couple other modules. We're going to be looking at what the AMD GPU and MPI modules are a bit later. But if you want to see when we load a module, what does it actually do? We use module show Julia, the big data version. We just let it show us the default one. Here it gives us, this is the Lua code that loads when the module command or module load runs. For example, here it adds various paths to the manual path and this Julia depot path, which controls where different where you install files or install Julia packages and where you just look for packages. And the load path does also something similar. There's also this CPU threads and num threads values. Here we actually want to use this raster raw flag if we really want to see the actual code. Somewhere here. This is the raw code. This might be useful to look at. Weight sets the number of threads is that it gets. It looks first if you have defined the num threads, it just uses that. Otherwise, it uses this default num threads, which it gets from the Slurm CPUs per task environment variable. If that isn't defined, it just sets it to 1. Anyway, then we load Julia. It will set those environment variables, and that should make Julia available on the environment. We use the module list command view and list all the loaded modules there. We should see Julia, and then we know how it does that. We actually have Julia on the path. It shows that it is on the path. Yeah, this demo is pretty much what I showed you, but there's a couple other modules which are these Julia-MPI and Julia-AMD GPU modules. Those are used for setting these so-called preferences to the path. What they do is that when at runtime, if you want the MPI.jl, this the MPI bindings for Julia, that will be covered. MPI complete will be covered in the later section as well as the AMD GPU, but this is just useful to know in the cluster environment that this module, it sets couple of these Julia load paths to a project.toml file that defines preferences that tell Julia when you're using MPI.jl and running MPI jobs to use the system MPI installation instead of when you install MPI.jl, it will install otherwise these external binaries as artifacts and use those. Whether you want to be using the system MPI or not, you probably on a cluster want to be using the system MPI. It should be kind of the fastest and fine-tuned, but for example, on your local computer, you just use the artifacts and forget about these things. The AMD GPU module, Julia AMD GPU module does the similar thing. It tells Julia to use the system AMD GPU installation. I'm not actually sure what is the current latest stage on using AMD GPU. If you have AMD GPUs on your local computer, you may have to manually still install ROC and those. For CUDA, Julia package manager should be able to install the right libraries as artifacts so that you don't need to set up anything to use local installations, but those are necessary and useful on a cluster. And if you're really, really interested in what is in those environments, you can look at this repository where I basically have all the installation scripts. If I show you very quickly, maybe the API thing on Lumi, there's a module that sets a few paths sets a path to this project.toml file that has this MPI preferences. This is the package, and these are the preferences. Tells it to use mpitch and libmpi crane. Also, this is quite important. It tells it to use the right MPI exec command to run MPI jobs. In the Slurm clusters, it's usually integrated with Slurm, so it's the srun command. Anyway, let's move on. Installing packages on a cluster. Install packages normally using the package manager. There's no difference basically. But there are maybe a few things that we want to do. We want to use usually multiple threads. Well, we have multiple threads available on the login node, so let's use those. And then on a Lumi, if you want to initiate your environment here, you'd want, at least for the next sessions, you would want to install the mpi.jl and amd.gpu.jl modules. If you want to try Dagger or cluster managers, you can install those. Unfortunately, currently, cluster managers could be used to run those distributed jobs on the multiple nodes, but last time I tested it gave some errors there, or probably some access rights to sockets or some issues, but you at least want to be installing the mpi.jl and amd.gpu.jl, then using the pkg's precompile function to precompile those modules so you can run those example codes. It's fine to install them in the cluster's default environment. Usually in your home directory, the default directory where Julia installs all the packages is the .julia directory in your home folder. And you can install them there. They don't take that much space or that many files. You may sometimes want to check the spaces command to see how many files you have installed into your home directory. These packages don't install that many files, but some packages like plots and some plotting related and visualization related packages may install tens of thousands of files. So be careful when installing those in the home directory. You might run out of quota. In those cases, you want to change the Julia depot path to some directory in ProYapple, for example. But most other packages are fine to install in the home directory on the cluster. They're on there, yes. Those shouldn't be .jl. They should be just without. Yes, good that you corrected. I will need to change that. Yeah, without the .jl. Yeah, let's look at the running interactive jobs, the cluster. Well, we can use srun with some resource options, and then this does as PTU to give us a interactive terminal, and then the terminal that we want to use, or the command to run a terminal that we want to use, in this case, bash, to run an interactive job. So similar to what we see here when we logged with SSH into Lumi. So log out, on me it says SSH Lumi, although for you, your command might need to put your username and the full address, but I have some SSH settings such that I log with that. That should log into the login node on Lumi, this one of them, the login node 4. Then we should be able to run these commands. This should be something that you can directly copy paste, and that will run interactive job on one of the nodes on the debug partition with 2 threads and 1 gigabyte of memory per thread, and time limit 15 minutes. We're using the debug here because it should give us the resources pretty quickly. It's usually not so congested. Whereas if we use something like small, we might have to wait for a while. Anyway, now here the node name changed. We are now on a compute node. Then you can use the environment normally. Same thing works for GPUs. Here it's just a different partition. We request 1 GPU, and then we request there are 8 GPUs on a GPU node on Lumi, so we request 1/8 of all the CPUs for the task. Otherwise, we're just kind of wasting resources. And this is also a way to get the interactive GPU job on a Lumi. We can use that later when running and testing GPU code on Lumi. We'll exit now that session. This should run normally. Yeah. It's the resource pretty quickly. Things should show us what we have requested here. Yeah. If you need to change partitions, you can look at partitions, for example, with this control command, or documentation usually has a list of partitions and a bit more readable form. But yeah, there's information here. It's not the most readable format, but if you want to quickly query things like partition names, you can also find them on the cluster. Then about batch jobs, so we want to send a job to Slurm, and then it will run when it gets the resources. We use the sbatch command with some options for resources, and then we supply some kind of shell script to sbatch that has the code that we want to run. Here we can try this example. Let's see. I will now create this batch.sh file, and then we should be able to run it with this command. Slurm will give us some output in the output file. Okay, it ran. Produce the hello world. This is one way to run jobs. The other way is to define the resource requirements straight into the batch file. It depends which strategy you want to use. This is a bit more general. If you ever need to change these programmatically, but if your resource requirements are rather static, then we can also specify them as these dispatch comments, and then it's possible to submit the job without any options. So that should also run. Let's see why that. Output here also quite simple. Exactly the same. We just request a different partition and one GPU to get the GPU resources. I will not demonstrate it here. There's nothing different compared to here. Then running Julia applications, when running on a cluster, we might want to we want to when we have our code, we want to define the dependencies in the project.toml. We may optionally also have the manifest.toml file, which gives us the full list of all the dependencies. And when running batch jobs, we want to use the specific project, so the specific project.toml file to run with those exact run our code with those exact dependencies. It's best that I demonstrate this. I remove this. We create our Julia script. This depends on the example package. Then we create the init.toml file. This is going to assume that we have a project or Julia application that has a project.toml file, and perhaps the manifest also given to us, and we want to run with those exact dependencies. Then we would load the Julia module and precompile, or sorry, instantiate the environment. Project, this will install all the dependencies of that project. Here when we supply this dash project and the folder, in this case the folder that we are in, it is same as we would use PKG's activate function on a directory, but this is a bit more convenient. And this E flag is just to execute Julia code from the command line. Nevertheless, that makes sure that it has installed the dependencies, which is the example package in this case. We usually want to do this instantiation on the login node before running the code on a compute node. Although you can basically do on the compute node if it happens that the instantiation has to start installing or precompile a whole lot of packages, it might just waste your resources from the job, or the compute nodes may run out of temporary memory because they're on a compute nodes the /temp, which is the default temporary memory, is usually quite small, something like 250 megabytes, which the package manager uses. And if it's installing a lot of dependencies, it might run out of that. Although there are ways around that by setting the temporary directory to somewhere else. But nevertheless, you want to do the instantiation usually on the login node before running. And then we can use this batch script to actually run the code on a compute node. Here, yeah, so the command for me is bin. And save this file. Then use sbatch. Sbatch and supply the batch script. Now it will start the job. Using tail-f flag, we can follow this file and wait until it has executed and executed our code. Should return hello. I probably should have put print line. Okay. Now it's printed hello world. That is what we wanted. But that is only one way to run Julia applications using the isolated environments rather than using the default. That's just a good practice to keep messing up with dependencies. But I think now we can move to the exercises. There are, I can give a little briefing. There are exercises for running multi-threaded job on Lumi, also running a single node distributed job on Lumi, as well as small MPI code and GPU code. You don't yet need to know what these codes does. You can just try running them. And there's a solution if you are stuck on something. Job and GPU job will be helpful for the next sessions where you may want to use Lumi's resources to run the MPI codes or the GPU codes. And you can also run this in batch jobs, or actually, MPI jobs you need to run as batch jobs. The other jobs, you can also try interactive jobs to run them.
So in some of the earlier episodes, you got some kind of a taste of MPI, but I thought that we could try maybe to demystify it a bit what it is. So MPI stands for Message Passing Interface. And if you look it up on Wikipedia, it will say that it is a library or a standard for programming of parallel computers. In practice, what this means is that MPI is a way for processes to communicate among themselves. And it is used to launch parallel or to execute parallel programs, mainly in the scenario where the data doesn't fit in the memory of a single program, of a single computer, sorry. So it is a type of distributed memory paradigm. What does this mean in practice? In practice, it means that an MPI-aware program can be launched with through an executable that can be called MPI run or MPI exec. And what this will do is to spawn several processes that share the same code. So it is basically a way of having multiple copies of the same program running that can sit on the same computer or different computers in a network, such as nodes in a cluster. What MPI does behind the curtains is to assign to each one of these programs a so-called rank that is like a unique identifier of each program. So you have ranks that are numbered from 0 to however many ranks you have. And these ranks are independent of each other. So they're separate processes with a separate memory space, and they can be multi-threaded between themselves, but in many ways, they're separate programs. What they can do through MPI is communicate and share data. And the way this happens is through message passing. That's why it's called a message passing interface. So typically, these processes communicate by sending chunks of data to each other. And in many ways, it is similar to the distributed module of Julia that we saw in an earlier episode. But it allows for much finer control of the execution, because through distributed, especially if you use the classic like PMAP type of paradigm, we are sending data to each one of the processes, and then we just fetch it back. With MPI, we have to manage the communication on a much deeper level, because we can send messages from one rank, and the receiving rank has to receive it. So we have to manage both sides of the communication, in most cases at least. There are also types of one-sided communication, but the general idea is that we have to take a lot more care in managing communication between the processes. And a common gotcha with MPI is the following. All tasks typically run the entire code. So since the processes that are spawned by MPI are copies of the same, they will all execute the same thing. So we as developers, we have to take care of making sure that not all the tasks do the same thing. A common example is printing. If we have a print in our code, then all the ranks will print it, but sometimes we only want what we call the master node in distributed Julia to do the printing. So you will see that our codes will contain a lot of if rank equals 0, do something, and the other ranks have to do something else. All the ranks are peer in MPI, so there is no master and workers as we have in distributed Julia, but usually rank 0 is considered kind of the master rank. So it's the rank where most where the values are collected, and it was one that does the printing. But there is in principle no reason why it should be rank 0. It's just common convention. We have here an example of a hello world in MPI, and we will go through it in a second. I just want to look at first how MPI works on a supercomputer. So if you tried the exercises before, you can see that you can add this mpi.jl module, package to Julia. And this can either come with its own MPI binaries, or it can fall back onto the system provided MPI. And usually on HPC clusters, that's the option to go for, because the MPI distribution that is on the HPC cluster is tailored and optimized to work on that particular cluster. Oftentimes, we will need to load an MPI module to be able to take advantage of MPI. This is not the case on Lumi. So Lumi, the MPI modules are already loaded at the login. They're part of the default set of modules that are loaded. So we can look at how we can add the MPI package in Julia. So we'll do what we have done throughout this workshop. So with this, I can use the local CSC files that Jan basically provided for us. And then I can load Julia. And in this case, it's quite nice to load Julia MPI that basically contains a set of preferences that allow us to take more advantage of the MPI distribution that is on Lumi. What it does is basically create this file for us, and it contains which library Accelerator is going to use and how to have GPU-aware MPI and other nice things. So this module just sets some preferences for us. Then I can start the Julia. REPL. This first instance will take a while. Now, in this case, I've already done it before, so this will not do anything, but I can do add MPI, and it will just most likely tell me that it's already present in my environment, or that this was already downloaded. Yeah, precisely. So yeah, it will just take some time, as usual, with the first time that we're running something in Julia to compile things. But in the meantime, we can look at this Hello World MPI program, and we will then execute it actually on several processes. So using MPI, of course. Then we have some boilerplate initialization of MPI. Then what happens afterwards is the creation of a so-called communicator object. This is basically what MPI uses to say that there is a ring of processes that can talk to each other. So usually upon initialization, there is this COM word that is a common, or like this the basic communicator object that MPI has that contains all the ranks. In some more advanced or complex codes, it can happen that there are several communicator objects instantiated. So we have groups of projects that can talk to each other, and they are separated from others. In this case, everything belongs to the word communicator. Then we can get the local rank of this process. So let's say that we launch, for example, this script with 4 processes, then we will have rank 0, rank 1, rank 2, and then rank 3. And for each one of these processes, the rank variable will have a different value, since there are several copies, but each one is initialized with a certain value of the rank. The size is the size of the communicator. So in this case, if I launch it, for example, with 4 processes, this will be 4. If I launch it with 5, it will be 5, and so on. And then the hello word is literally an hello word. So this will print hello from each rank out of the size of the ranks that we have. And then we put a barrier. This is basically to say that at this point, post execution, wait for replies from all the ranks, and then you can safely quit. And we can give it a look. So I will go to my folder where I copy the script. This was for 5.00.13.10. And then there's me, MPI Julia. And I have in here the hello word MPI that contains what we have there. So the way MPI programs are launched is through an MPI launcher. This can be different depending on which cluster we are on. So, for example, on some clusters, we will find that the command is called MPI exec. On some others, called MPI run. On Lumi is srun, so the one that you're familiar with. And to simplify this, Julia allows us, and you can see this in the setup section, to define an MPI exec JL that is just a theme wrapper on whatever MPI command we want to use. So if you're using the system the system API, this can fall back on the system API distribution. If you use some of the precompiled ones the Julia ships with, it can fall back on any of the distributions that it comes with. In this case, I could just go with a plain srun. So for example, I can try with 4 processors, so 4 processes. And then I go Julia, hello word, MPI. And this will have to queue up, but already ask for a reservation. So what it did is basically spawn 4 copies of the process, each one with a different rank. So each one of them printed for me, I am rank 0, I'm rank 1, rank 2, rank 3. And these processes can sit on the same computer or on different nodes. It doesn't make a difference as long as they can communicate with each other. And it is Slurm, our workload manager, that makes it so that the processes know who they are. I can do the same thing, for example, with just 2 processes. And, oh, this was probably still running. This is probably still being held by the process there before. Never mind. But yes, so I can spawn as many processes as I want, given that I have an allocation for it. So as I told you, this is the communicator object. So my ring of processes that talk to each other, each rank, and the total number of ranks. Now, how can we get these processes to actually talk to each other? There are a lot of communication functions, as we can see in the reference of the MPI.jl package. But in principle, there are 2 types. One is the so-called point-to-point communication. That is basically saying that among our ring of processes, we pick 2 of them, and process A, for example, in this case, sends a message to process B. So this is called a blocking point-to-point communication between 2 ranks, because process A basically calls the send function and can send some data that it wants through mpi.send. And process B has to be ready to receive it, So we have to call MPI receive. And this is quite different, for example, from the distributed pattern where we have to only manage one side of the communication. We can also have, or actually we can give a look at it now. So we have send, receive, and the code is also down here in your example if you want to look at it. We have the same boilerplate. And this is what I was telling about. So in this case, we're distinguishing if the rank is 0 or if the rank is not 0. So all the other ranks will send a message saying, hello world, I'm rank with this number of rank. And this is how we call the function. So we have mpi.send. The message is this string in this case. We're sending it to someone that is on the same communicator that we are in, that in this case is the com word. And then we pass it the destination. So the destination is the rank of the process that we want to whom we want to send our message. The tag is something that can be useful in some cases. It's like a label that a message has. So for example, if processes exchange different things between each other, we can tag them so that whenever a process receives a message, it knows what it is about, kind of, because we can use the tags as a kind of labeling system for the messages that we send. Then if we are rank 0, so all the other ranks send, rank 0 will, for each sender, receive the message. So again, we pass it the communicator, and we have to make sure that the source is the one that we're expecting it from. So in this case, we have just as many senders as other ranks, and the tag again. And then we can print this message. So we have to manage both sides. And in Julia, for both MPI send and MPI receive, there are also in-place version. So the version of this that also contains exclamation mark. If you use this version, then we have to put here the variable in which we're going to write. So this is in place because we're already passing it a buffer, and we're telling it, look, we would like our message to be written here. So this is called point-to-point communication. And in this case, it's called blocking, because the MPI send will only return up when the message can be received. So it's kind of waiting for a confirmation that the message was received. And how this behaves is different across different MPI distributions. And we can, we'll show you an example in a few minutes where this can actually matter. So let's try to execute this. For example, we can choose 3 processes here, and we say Julia send receive. And in this case, we're saying what I told you. So rank 0 is the receiver, and is printing the messages that is received from rank 1 and rank 2. Once again, yeah, we can pass it whatever number of n as long as we have enough processors to run this, and this will scale exactly the same. This is nice and useful, but a lot of times we need not point-to-point, but point-to-many or many-to-many type of communication, meaning that we can have several processes that are sending the same thing to one rank, or one rank that is distributing work among many different nodes. And MPI provides some primitives for this called collective communication functions. And there are a few types. So one of them is called gather. So let's say that, for example, each rank does some piece of work. Then all of them, they can send their results to one rank. So in this case, all ranks send their data to the rank that we call root. We can have scatter that is exactly the same. So the data on one rank is split into several chunks that are sent to all the other ranks. And the scatter gather type of behavior is what distributed and pmap do. So when we have, spawn at and fetch, this is kind of the same logic. So our array is divided in chunks, or our data, wherever shape it is divided in chunks. Then each rank performs the computation I need to perform, and then they're all gathered back into the rank that originally sent them to. We can have broadcasts, and it's kind of similar to the scatter, except that the data is not divided, but is simply copied to all the ranks. So in this case, you can see that for the scatter, we had 1, 2, 3 that are divided to different ranks. In this case, we have only one that is copied across all the ranks. And then we have reduce is the last, or one of the last collective communication primitives. And this is kind of a gather, but rather than collecting all the data on the node, it performs a kind of reduction. Reduction in this case means that, for example, each rank does a computation, and then we can all get them summed on rank 1. It can be a sum, it can be a product, it can be min, it can be a max. There are many pre-built reduction operators that come in MPI. And moreover, a developer can also define their own. And we can give a look at many of these operations. So we have, for example, this is lagging quite a bit. We can look, for example, the scatter. So in this case, the 0 rank, we have the usual boilerplate as before. If the 0 rank will send an array that is basically a number from 1 to the size of the communicator elevated to the third power. And all the other ranks are not sending anything. And then the rank, or in this case, it's a collective operation, all the ranks will receive a chunk of this array. And so the rank 0 will send this send buffer, and all the others will receive it. We have to give it the type of variable that we're expecting. And we have to know who the sender is. So who is the rank that is scattering all the initial data. So we say the root is 0. And then all the ranks will say that they will have received a certain chunk. So we can run this, for example, with 4. Yes. So we had an initial array that went from 1 to 4, and we elevated it to the cube. So we have 1, 8, 27, 64. And each one of the ranks received a chunk. And in this case, the chunk was one single number. The scatter primitive expects chunks of the same size, but a lot of times the number of the amount of data that we have is not exactly dividable by the number of jobs. So for those situations, there is a scatter v primitive as well, scatter variable, that takes instead chunks of different sizes. So this was the scatter. We can look at the gather that does exactly the opposite. So each rank will send its own number to the third. So it's exactly the opposite as before. And the rank root that we're saying is 0 will collect all of those. And now we can print basically for each one of the received chunks what we got. So we can do the same with 3, for example, Julia, gather. And this is telling me the same. So I got from each rank, the main rank received the number to the third. So these are kind of the primitives that, we can show the reduce that I forgot. In this case, the piece of data that we're sending is the rank number, and the receiving, the main rank or the 0 rank will sum all this data. So we pass it the data that each rank is sending, the reduction operator that we want to use, in this case is a plus, and as usual, the communicator object, and where this data needs to be reduced. So in this case, we send it to rank 0. And let's do this again. For example, with 2 ranks, so the sum will basically be only 1. Yeah, it sum up rank 0, rank 1, and it gave me 1. So this lets us implement the communication logic between the processes. One thing that we can mention is that for each one of these send and receive methods, we have also a version with uppercase. What is the difference? The difference is that the lowercase send and the lowercase receive can communicate any type of object, including, for example, complex structs that refer to other objects. This is because they are serialized. But we can also send, just the plain data as it is, that is much faster. But that means that we have to know beforehand how much space we need to reserve for it. And these methods are usually faster, but yeah, we need to take more care in using them. And usually they start with uppercase letters. The main difference basically sits in the type of data that we want to send. So for any primitive type, including structs, as long as they're based on just primitive types, we can use the uppercase. Otherwise, we need to go back to the lowercase. And as I told you before, for all these methods, we have both the in-place version, so the one that mutates the buffer that has been sent, and also one that is allocating. So one basically returns something, this one. So we say variable equal MPI rec. And the other case, we modify in place a buffer that we pass to the function. Yes, it is. Here you can find the examples that I've shown you. Now I would like to go back to one problem that I cursorily mentioned before, that is blocking or non-blocking. So the normal MPI send and MPI receive, they only return when, in the case of MPI send, when the program basically releases the send buffer, and the MPI receive would only return once the data has been received and written to receive buffer. This is to say that basically MPI send will wait for a kind of confirmation that the message has been actually delivered, and MPI receive will only return when it actually has been received. And this can very easily lead to some kind of deadlock. So, because both of them, they can basically be stuck waiting for a confirmation that the other is sending. And this can lead to a circular dependency that it's hard to come out of. And these examples here shows exactly this. So in this case, we have to run this with 2 ranks, and rank 0 will try to communicate with rank 1, and vice versa. So rank 1 one rank will try to send a message that is a read to the other, and while the other one waits. But both of them are executing these exact instructions. So both rank 0, rank 1 are, sending and receiving. And they can be stuck in a loop of waiting for each other. Now, in many cases, and for most MPI distributions, this might not be a problem if the messages are small, because MPI can implement a sort of buffering system where basically send can return even though the message has not been received yet, because there will be a temporary buffer where this sent message is stored. So for example, if I try to run this now with 2 ranks, Julia deadlock, this will actually work. But if this message was much bigger, for example, I couldn't fit in a buffer, this could lead to a deadlock. And there are a couple of workarounds to avoid situations like this. One is with so-called non-blocking type of communications, and these are shown in this non-blocking solution here. So the situation is the same. We have 2 ranks that are trying to send messages to each other. And we have this so-called non-blocking send and non-blocking receive. These are, for those who are familiar with it, asynchronous calls, they're called. So the I send will send and then immediately return. It doesn't care if the message has actually been received or not. It will send and leave it at that. And the MPI I receive is kind of like a promise of receiving. It basically saying, okay, I have a listener here that is waiting for a message, and you can go back to your work. So these ones will be called in an asynchronous manner. And then to make sure that at some point these messages actually land, we have to use this wait all method. So if you remember the distributed, this is kind of like fetching from a future. So they're both saying that there will be something there, and then at some point we have actually to collect these results, and we use the wait all. And in many cases, it's easier to use this kind of non-blocking solution to communicate. In this particular case, since we only have 2 ranks, this can be kind of worked around by distinguishing what the different ranks are doing. So in this case, if the rank is 0, we make it send and receive. And if rank is 1, we make it send and receive. So in this special case, we only have 2 ranks, exchanging a simple message. We can actually work around it. But when we have more complex topologies, non-blocking communication is the way to go. And yes, I think this makes for a nice introduction. So yes, you have a lot more, fine-grained control on how the processes talk to each other compared to simply just splitting an array. But this, of course, entails much more workload from the developer side to take care of this communication. MPI is also lets you do some cool things, for example, on Lumi, but also other clusters. There are GPU-aware MPIs. So basically, you can have GPU communication where the messages are passed from one GPU to the other. So this can be an interesting use case when you want to parallelize over several GPUs. Tomorrow we will see examples of one, but through MPI we can have several GPUs computing in parallel. I think after this there are some exercises, and you can try to, for example, to run the examples that are in this folder yourselves. You can do it using a batch script. So taking from what Jan showed you in the episode before this one, you can have a batch script where all your batch calls, and then just in the end, let's run Julia. Yes, so you can rerun these examples that we had before. There is one very interesting example that I would suggest you to look at, and this is the compute pi that was also featured in some earlier episodes by throwing darts. And in this case, since the processes do not share the same memory through MPI, they have basically to send messages to each other. So I think this is a quite interesting example that I really invite you to go through. And yes, I think that's it from my side for now. So I guess it can be time for exercises.